Lesson 3 is a discussion of data variability, or the spread of the data values. Consider the data sets A and B. If you calculate the mean, median, mode, and mid-range, you will find that they are all equal to 5. So what is the difference between these two sets of data? The answer is variability. There is a change in variability between the two data sets. Set A has some variability, while Set B has no variability. One way to think about variability is to examine how far each data value is from the mean. We anticipate that the measure of variability will be 0 when there is no variability, as in Set B. If the spread of the values around the mean increases, then we anticipate that the variability will increase, as in data set A. The first measure of variability is the range. It is a simple calculation. Subtract the lowest value in the data set from the highest value. In set A, the highest value is 9 and the lowest is 1. We simply take 9 minus 1, which gives 8. Set B has no variability since 5 minus 5 equals 0. The advantage of calculating range is that it is an easy measurement to take. You simply need the largest and the smallest numbers to complete the calculation. Also, no conversion between units is necessary, therefore, the range is always in the same units as the observations. There are several disadvantages when using the range as a measure of variability. For example, since it is simply a subtraction, it does not take into account the number of observations in the data set. The larger the data set, the larger the incidence of including extremes. Extreme values yield a larger range and may be misleading. Even though the majority of the numbers in the example are quite low, the range is 30. Comparatively, the range is much larger than most of the numbers in the data set. This gives a false impression of the data set. The range has a potential to be influenced too much by extreme observations. The mean deviation is the average of the absolute deviations from the mean. Notice the upright bars within the formula. These are the absolute value signs. Any calculation performed within the absolute value sign will always be a positive value. So even if the calculation within the absolute value sign yields a negative number, we will always change it to a positive. As we can see, the mean deviation for set A is 1.67 and for set B, 0. The next slide details a table to aid in solving the rest of the equations in this lecture. This type of table can be very useful in solving most summation problems. For mean deviation, set up a table containing the x's highlighted here in blue. The x sub i's minus the mean without taking the absolute value, and the x sub i's after taking the absolute value. Now that we know the sum of the third column is 10, we simply divide by n, which is 6, to arrive at 1.67 as the value. As with range, the mean deviation does not require conversion of units, so the units are the same as the units of the data values, and it is not affected by extremes as much as range. This is because we subtract the mean from each observation. The introduction of the absolute value makes analytical calculations very complicated. The most widely used measure of variability is the variance. The formula for variance is the sum of the squared deviations from the mean divided by n minus 1. Each x sub I minus the mean is a deviation from the mean. Use the table method to solve variance. One must simply find the sum of the x sub i's minus the mean squared. The sum is 34. Once we solve the formula, we see that the variance equals 6.8. The number of observations minus 1 is the degree of freedom. Note that we must calculate the mean in order to calculate the variance. Try not to get caught up in this lengthy definition of degrees of freedom. The example coming up should explain the concepts adequately. The key idea when working with degrees of freedom is independence of information. Let's suppose that our earnings are $10,000 and our payments are $8,000 and our bank account balance is $25,000. Knowing either one or two of these pieces of information will not aid in deducing the others. Our bank account balance does not depend on our earnings and payments. These three pieces of information are therefore said to be independent. There are 3 degrees of freedom. Now in this example, if we know any 2 of these pieces of information, the third item can be determined. Instead of having 3 independent pieces of information, we now have 2. In other words, the degrees of freedom is 3 minus 1, or 2. Now take a moment to pause the slideshow to review the definition of degrees of freedom. When you are finished, review the 2 videos of Dr. Vizcarra's presentation on degrees of freedom. Here we see a more convenient computational formula for variance. This formula, although it looks harder, is actually faster to solve. The problem when using variance is that we work with units that do not match the units of the data set. For example, if our data set are weights in pounds, then the variance will be in pounds squared. To overcome this problem, we take the square root of the variance to obtain the standard deviation. The standard deviation is always positive. Here we see the formula for standard deviation of set A. Simply place the variation formula under a square root sign to find the formula for standard deviation. In order to solve this equation, remember your order of operations. Please excuse my dear Aunt Sally is the acronym for parentheses, exponents, multiply, divide, add, and subtract in that order. First, we need to square all of the x's individually to get 184. Next, we add up all of the x's before squaring and dividing by n, which is 6. This gives a value of 150. So to solve the formula, first subtract 184 minus 150, then divide by the degree of freedom 5, and finally take the square root. The standard deviation of set A is 2.608. Once again, set B has a standard deviation of 0. Since the standard deviation is the square root of the variance, it has the same units as the observations in the dataset. Say we've just finished weighing a large group of cattle. We've just been informed that the scale was not tared and we need to add 5 pounds to each observation to correct the problem. This type of manipulation of data can be observed when adding a constant to all observations in the dataset. Adding constants increases the mean by the amount of the constant. In other words, the average weight of the cattle would increase by 5 pounds after making the adjustment. To take set A as an example, we simply add 2 to each observation and recalculate the mean. The new mean is 7, which is the same as 5 plus 2. Unlike the mean, adding or subtracting constants does not alter the variance or standard deviation. The standard deviation is not affected by adding or subtracting constants. If you recalculate the variance and standard deviation of set A, the variance is still 6.8 and the standard deviation is still 2.608. As with adding a constant, the mean is affected accordingly when multiplying observations by a constant. When each observation is multiplied by a constant, the new mean equals the old mean multiplied by the constant. For example, if we multiply set A by a constant of 2, our mean now becomes 10, which is the same as 5 times 2. When multiplying observations by a constant, the variance is affected in a peculiar way. The new variance is the constant squared multiplied by the old variance. Once again, if we multiply example set A by 2, our variance will be 6.8 times 2 squared, which is 27.2. Multiplying a constant by all observations in a dataset causes the standard deviation to be multiplied by the absolute value of the constant. Remember that the absolute value is simply the positive value of the constant. As shown here, multiplying set A by 2 is the same as multiplying the standard deviation by 2. If we need to multiply by negative 2, we simply take the positive value of negative 2, which is positive 2, and multiply it the same as the previous example. This concludes Lecture 3.